In this video, we are going to review a full repeated measures ANOVA problem. And so we'll walk through the problem, look at the key indicators for why we're going to use repeated measures ANOVA, and go through the whole hypothesis testing process, along with how to do this in Jamovi. So here is our example problem. The following data were obtained from a research study examining the effect of sleep deprivation on motor skills performance. A sample of 5 participants, and I'll go ahead and just highlight this. A sample of 5 participants was tested on a motor skill task after 24 hours of sleep deprivation, tested again after 36, and tested one more time after 48. The DV is the number of errors made on the motor skills task. Do these data indicate that the number of hours of sleep deprivation has a significant effect on motor skills performance? So, a few things that we should take in mind. We have a sample of 5 participants, and those participants are being tested after 24 hours of sleep deprivation. They're tested again, and they're tested once more. So there are 3 conditions. And because each participant is contributing a value in each of those conditions, and we have more than 2, that is what tells us that we need to use a repeated measures ANOVA. All right. So the first step in our hypothesis testing is to list our null and our alternative hypothesis. So the null hypothesis is always a statement of no difference or no effect. So here we can write this as mu1 equals mu2 equals mu3. We have 3 mu's because we have 3 groups, 1, 2, and 3. And so in words, we can state that there's no differences among conditions, or sleep deprivation has no effect on motor skill performance. But again, we need to write this in terms of mu because in inferential statistics, we are recruiting and sampling individuals to say something about the bigger population. Our alternative hypothesis is that at least one mean differs. So we can say that there is some difference. We're not specifically predicting whether mean 1 is going to be greater than mean 2 and mean 2 is going to be less than mean 3. All we need to say for an alternative hypothesis is that at least one mean differs. Now, this question doesn't give us a specific alpha value, but we'll go ahead and assume it's alpha of 0.05. And so when we know this, we know that we're going to be looking for our F distribution at a 0.05. And to get our critical value, we need to know our degrees of freedom. So in order to get our degrees of freedom, I usually like to solve for this first since it's pretty simple. We don't need to do too many calculations here. And if we have the data before us, we know exactly what we have exactly what we need. So to get our between groups degrees of freedom, we simply solve that as k minus 1. K in an ANOVA just represents the number of groups. So we have 1, 2, 3 groups. So 3 minus 1 is 2. The between persons the between persons degrees of freedom is lowercase n minus 1. Lowercase n in a repeated measures ANOVA just refers to the number of people that we have. So how many people do we have in our study? That is 5. So 5 minus 1 is 4. Now, to get our error degrees of freedom, we multiply our degrees of freedom for the between groups and the between persons. So k minus 1 was 2. N minus 1 was 4. 2 times 4 is 8. Now, we know that the total degrees of freedom is partitioned into these 3 components: between groups, between persons, and error. And we know that these 3 terms will sum to give us the total. So if we sum these up, 2 plus 4 is 6, plus 8 is 14. We know by just addition and subtraction that it should be 14. But we can also confirm this. So k times n, k is 3. N is the number of people. So again, we have 5 total people. K times n, 3 times 5 is 15. 15 minus 1 is 14. And again, 14 is broken down into 2, 4, and 8. Now, which of these degrees of freedom values do we use to find the critical value? Well, we need to use the between groups and the error. So we're going to look at our F distribution table, and we are going to find at an alpha of 0.05 what our critical value will be for a between groups degrees of freedom of 2 and an error degrees of freedom of 8. So here's our F distribution table. And so we can see that our degrees of freedom numerator is that between groups portion. So we're going to use the second column, and we're going to go down to where the error or the denominator degrees of freedom is 8. And remember that in this particular table, the unbolded value is going to be our 0.05 level of significance. So 4.46. Okay. So 4.46, and in this table that I got this one from, it took it out to 3 decimal places. But 4.459 or 4.46 is our critical value. So again, if we come up with an F value, an F ratio that is greater than 4.46, then we have evidence to reject our null hypothesis. So what about the calculations that we need to do? Well, we've already done our degrees of freedoms, right? And how do we solve for variance? Variance is just sums of squares over degrees of freedom. So you're already halfway there just by doing very simple calculations for degrees of freedom. Now we're going to solve for our sums of squares. Remember that the sums of squares total is partitioned into its 3 components. In a repeated measures ANOVA, those are the between group sums of squares, the between person sums of squares, and the error sums of squares. So our total sums of squares is done using the formula that we have used before, sum of x squared minus the sum of x's squared over n. This is the total, so we're going to be using all of the x values. So 0 squared plus 1 squared plus 0 squared plus 4 squared plus 0 squared plus 0 squared plus 3 squared plus 1 squared plus 5 squared plus 1 squared plus 6 squared plus 5 squared plus 5 squared plus 9 squared plus 5 squared. This gives us a sum of x squareds of 245. To sum the x values, here, we're just going to sum up all the scores. So this is 0 plus 1 plus 0 plus 4 plus 0 plus 0 plus 3 plus 1 plus 5 plus 1 plus 6 plus 5 plus 5 plus 9 plus 5, which gives us 45. And plugging those values into our formula, 245 minus 45 squared over 15 is 135. That gives us our total sums of squares of 110. Now, what do we know about this? We know that 110 is going to be broken into 3 different parts. These 3 parts will need to sum up to 110. So it's always good to do your total sums of squares calculations first so that you can just make sure you check along the way whether your sums of squares that you're computing for these other components make sense. So let's go ahead and now do the sums of squares between groups. We have our sigma notation outside the bracket. Sigma just means to sum. We're going to sum everything inside this bracket. In ANOVA, we know that K is equal to the number of groups. And so we know that K is 3. We have 1, 2, 3. So there are going to be 3 components to the sum. We are going to sum up the X scores in each particular group, square that sum, and divide by the number of scores. So 5 squared, because we get 0 plus 1 plus 0 plus 4 plus 0. So the sum of the scores in the 24-hour group is 5. 5 squared divided by, and there are 5 people. 10 squared, we get 0 plus 3 plus 1 plus 5 plus 1, which gives us a sum in the 36-hour column of 10. 10 squared over 5. And then we have 6 plus 5 plus 5 plus 9 plus 5, which gives us a sum of 30. 30 squared divided by 5 is 180. We add those up because, again, we're adding up everything in the bracket. That gives us 205. But remember that we have to also subtract this component here, which we've already written in the sums of squares total, which is 135. This is the part where if you are trying to get in a rush and you forget to do this, you would see that 205 cannot be a smaller component of 110. So we know that the between group sums of squares is 70. So we know that 70 is less than 110. So far, we're pretty good. Now to solve for the between persons sums of squares, we are going to multiply the sum of these squared row deviations by the number of groups that we have. So in order to solve for this between persons variation, we need to first come up with a row average. The row average just says that for each particular participant, what was their average dependent variable value across all of the conditions? So for person A, we have 0 plus 0 plus 6. So 6 divided by 2 gives us, or 6 divided by 3 gives us 2. Person B, 1 plus 3 plus 5 is 9. 9 divided by 3 is 3. 0 plus 1 plus 5 for person C is 6. 6 divided by 3 is 2. 4 plus 5 plus 9 is 18. 18 divided by 3 is 6 for person D. And E is 0 plus 1 plus 5. So that's 6 divided by 3 is 2. So these values here, and I'll go ahead and highlight these values here are what we refer to in this Y bar row, which just means the average for each particular row. So there are 5 of these values, meaning that there's going to be 5 components to the sum. The grand total, Y bar just stands for the mean of the Y values, with the T subscript just means the total average. So this means if you were to add all of these scores up, all 3, 6, 9, 12, 15 scores up, add it and divide by 15, you would get your total, which in this case is 3. So 2 minus 3 squared plus 3 minus 3 squared plus 2 minus 3 squared plus 6 minus 3 squared plus 2 minus 3 squared gives us 12. Now, before you go and put 12 down as your sums of squares between persons, because it's less than 110, and when added to 70, it's not greater than 110, you must multiply that sum value. You must multiply that sum value by k. Now, the reason why we multiply it by k is because we have 3 conditions. And the between persons component is dealing with the fact that everyone is the same across these conditions. So we multiply this sum by k. So 12 times 3 is 36. So this gives us 36. Then we can just use subtraction to say 110 minus 70 minus 36 leaves us with a value of 4 for our sums of squares for error. And once we have these terms, what we can do is just fill in our ANOVA summary table. We again have source here on the left. Then we have our sums of squares, degrees of freedom, mean squares, and our F values. So treatment, sums of squares was 70, error was 4, between persons is 36, total 110. Now, like I mentioned before, not every program will include the between persons as its own row in the main summary table. Jamovi doesn't. So you don't necessarily have to include this directly in the table, but for our sakes, we can for now. Remember that sums of squares divided by degrees of freedom gives us variance. Mean square is also referred to as variance. So 70 divided by 2 is 35. 4 divided by 8 is 0.5. And these two are the components that we're interested in. The variance for the between groups divided by the variance within groups gives us our F ratio here, which is 70. So we can look at 70 and say, well, where's 70 in relation to 4.6? Well, 70 is way out here, right? Because remember that these tails are asymptotic, meaning that they'll never touch 0. They go off to infinity. And so 70 is definitely in that shaded region. So the decision then is to, do we reject or retain? And the answer is we reject. We reject the null hypothesis. But remember, in a conclusion statement, we always need 2 sentences. The first tells us whether we are rejecting or retaining. And the second sentence says, what does it mean? What's the context? So we can then say that there is sufficient evidence to claim that sleep deprivation has a significant effect on motor skills performance, comma, p less than 0.05. We can add this statement p less than 0.05 because our alpha value was 0.05. This shaded region represented the top 5%. To follow up this significant p-value, we can do our post hoc tests, but also we can solve for the effect size, which is eta squared, interpreted as the percent of variability or variance in our DV that can be explained or accounted for by our IV. And you can just substitute your DV and your IV respectively. So here we take our between groups sums of squares, which we have as 70, divided by our between groups plus the error. So 70 divided by 74 gives us 0.946. We then multiply this value by 100 to give us a percentage. So 94.6% of the variability in motor skills performance, again, that is what we're measuring, can be accounted for by sleep deprivation, or rather the errors made on the motor skills task can be accounted for by sleep deprivation, that being our independent variable that we had here. So how can we do this in Jamovi to confirm that our calculated values are correct? So when we are working with repeated measures ANOVA specifically, the levels of your within subjects variable are going to be your columns. We do not need a categorical variable column because everyone is participating in every one of those conditions. So here, we're going to have each of our levels serve as a column. So in Jamovi for repeated measures ANOVAs, when you're setting up your repeated measures ANOVA, it should look similar to the data that you have before you. So we have each row represents a person. Each column represents a level, and we have all of our data present. So each row represents a different individual. And then each row, again, person number 1 had 0, 0, and 6. That matches what we had. Under the Analyses tab, we see ANOVA, and we're going to select Repeated Measures ANOVA, specifically for when we are dealing with designs where everyone is participating in every condition and we have more than 2 conditions. So when we select Repeated Measures ANOVA, the window looks a little bit more complicated than it did in a one-way between subjects ANOVA. So let's start with this top box here, Repeated Measures Factors. So in this box, you will define your within subjects factor. So RM1, you can actually hover over it and click it, and you can change the name of that to whatever it is that you are actually measuring in terms of your independent variable. So that could be level of sleep deprivation. So you will add the name for each level then that you have. Once you change this name, you can then add level 1, level 2, change the names there. Now, by default, Jamovi only gives you 2 levels to start. If you want to activate this 3rd level, you would simply click on this and hit enter. That would then make this level active. It's not that intuitive, but I have some additional tutorial videos that will help explain that. Now, this middle box called the repeated measure cells is where you're actually going to move your variables here on the left-hand side so that they are then matching based on the levels that you're defining. So level 1, level 2, level 3. In a true within subjects ANOVA, you won't have any between subjects factors. So in a true repeated measures ANOVA with just 3 levels, 3 or 4 or 5, etc., where you aren't also incorporating a between subjects nominal variable, you will only be using essentially these boxes above. Now, one thing that is important to do, and I've listed here at the bottom, is that you do need to name your dependent variable. So this dependent variable label just by default says dependent. You need to change that name so that your DV is properly named. So in the case of our study, we had the number of errors made in the motor skills performance. So here I kind of just show you what this looks like. I've renamed, again, that factor to hours of deprivation, 24, 36, 48. I then moved those specific variables to match the levels that I've defined. And then in my dependent variable label, I've given it a name. The reason why you want to give it a name is because when you produce a plot using Jamovi, Jamovi is going to use whatever you have in this box in your graphs. So our repeated measures ANOVA looks like this. We have our within subjects effects given in this table here. Notice here that you just have your between groups and your within groups. And then you have a separate between subjects effects, which represents your between persons component. Similarly to the one-way ANOVA, you do not have a total row. So notice here that our sum of squares, 70 and 4, degrees of freedom, 2 and 8, 35 and 0.5, our F is 70. This indeed matches what we had calculated by hand. And then here we have our sums of squares for the between persons, 36, 4, and then 9 for our mean square. Now, you'll notice here in your repeated measures ANOVA essentially worksheet or selection window, you can choose the effect size measure. And yes, while we have called it eta squared, technically we are going to select partial eta squared. Partial eta squared is going to allow for us to get that corrected calculation to give us the correct value for our effect size. So in the one way between subjects ANOVA and the one way within subjects ANOVA, the calculation for eta squared is slightly different. Now, again, the reason why it's different is because in a repeated measures ANOVA, we are taking out some of that error variability. And so that denominator is a little bit lower. Now, if you have a significant F value, just like we talked about in the between subjects ANOVA, we want to follow that significant value up so that we can actually say where that significant difference lies. So selecting the post hoc test drop-down menu, you'll see your specific variable of interest that can then be moved over. And by default, Jamovi gives you Tukey as the pre-selected value. For all intents and purposes, that is okay unless I tell you otherwise. Now, how do we interpret the post hocs? Just like we did with the one way between subjects ANOVA, we read from left to right. And so, for instance, in this case, and I'll change my marker color, 24 versus 36 hours, we read across the row, and we see that the p-value is 0.072. Is 0.072 greater than or less than 0.05? And it's greater than, meaning that it is not in that rejection region. So we can actually say that there is no significant difference in the number of errors made between 24 and 36 hours. Now, if we go from 24 hours down to 48, we're now comparing 24 versus 48 hours. And we go across the row, we see that there's a mean difference of 5, and we have a value of less than 0.001, which is indeed less than 0.05. So we say that there's a significant difference between 24 hours and 48 hours. With this mean difference, this is interpreting it as 24 minus 48, which is why this value is negative, because 48 hours had a higher average amount of errors made. Then we have the last row. We have 36 hours compared to 48 hours. We read across the row. -4 is the mean difference, and our p-value is 0.007, which is indeed less than 0.05. So if we were following up a significant F value, we would report, of course, the F, but we would also go and say follow-up post hoc results revealed that there were specific differences between 24 and 48 and between 36 and 48. Now, a great way to accompany those post hoc results is to produce a plot. The way to produce a plot in Jamovi is to select the estimated marginal means drop-down window. By doing that, you will be presented with your specific variables of interest that you have listed here. You can then move that variable into the term, and that will give you an output. Now, this is where you need to make sure you have labeled those factors and the dependent variables, right? So your DV label is going to be here on the y-axis. Your factor name is going to be here on the x-axis. And so you'll have by default a marginal means plot that will be provided to you here. The plot, you can change how the error bars are constructed, whether they're constructed with confidence intervals or whether they're constructed with standard errors. You can also select whether you would like the observed scores to be seen amongst the bar. And you could also request Jamovi give you a marginal means table. This is a really useful graph to get, or a plot to get when you're interpreting post hocs, because it helps you to kind of visually see. So for instance, we saw that there was no significant difference between 24 and 36 hours, right? The value was 0.072, so this is no significant difference. But we did see a significant difference between 24 and 48 and between 36 and 48. And so when you're working with post hocs and you are working with significant F values, it is really good to make a plot. In your final paper for this class, you will need to make a plot to illustrate your specific statistical findings. And it's through the estimated marginal means window in your specific analyses in Jamovi that you will be able to get that done.